Welcome, everybody. So we are going to be starting a new topic this week. We'll be talking about oscillations. So I am going to go ahead and walk us through the basics of how oscillatory motion works. You've already had a chance in your Get Ready activity to play around with the simulation and see some examples of oscillatory motion. The canonical one that we are going to use is a small mass attached to a spring on a frictionless table. You can see a picture of that on the shared screen here. What you will notice is that there is a spring, something we studied back in Physics 11, which has a known spring constant, little k. The block, which is attached to that spring, has a known mass, little m. And for this example, we're going to assume that we have stretched the spring so that it's been displaced from equilibrium by an initial distance x max and then released from rest. And you've already had a chance in the Get Ready activity to explain what you think is going to happen to the block. And we are going to try to throw some formal mathematics at this. A little bit of this math will be fairly advanced. We'll get into some differential equations, which you don't need to be scared of. I will never ask you to solve a differential equation from the beginning in this course. But it's nice to be familiar with some of the general rules of how they work. All right, so let's dive right in. Here again is my system. I'm going to start, like we do with many physics problems, by drawing a quick free body diagram for the block. So there is my free body diagram block. I know that I've got some vertical forces acting on this block. They would be the gravitational and normal forces. And then I'm going to have a force by the spring, which points to the left because this spring has been and I know because of what we did in Physics 211 that I can model the spring force as being linear and say that it is equal to minus k times x, which is the displacement of the spring. So at this particular instant in time, that x would be x max, but as the block moves from place to place, the strength of that force will change. And that's really important in what we are going to be doing. That is it. Those are the only three forces that are acting on the block. We're going to neglect things like air resistance and friction. And I can now use Newton's second law and see what it will tell me. So I'm going to go ahead and dive right in. I've got that prepared on the slide already here. I'm going to use F net equals ma, which is Newton's second law. I'm going to plug in the net force, which is in this case only the spring force, and is equal to minus kx. And then I'm going to leverage something I know, which is that the acceleration of an object is equal to the second derivative of that object's position. So d squared x dt squared. And then I'm going to do a little bit of solving and end up, as I warned you, with this differential equation. Now, if you've taken a differential equations course, you might recognize this as a differential equation, which is ordinary, linear, second order with constant coefficients. And there might be one that I missed in there. So this has a known set of properties, and we are not going to spend time in the physics class solving this from first principles. We're going to appeal to the hundreds of years of solutions to differential equations that have come before, and I'm going to kind of ask the mathematician version of myself for the answer, and the mathematician in me says the answer to this particular differential equation is the cosine function. So I know that basically anytime I want to take a derivative of something and get back to where I started, if I want to take two derivatives and get back to where I started, that's going to be sines or cosines. And an important feature of that is that there's this negative sign here. You remember how sine and cosine work. When you take the derivative of sine, you get cosine. And then when you take the derivative of cosine, you get back to negative sign. So that negative sign shows up when I take a couple of derivatives. Anytime I have sines or cosines show up, I want to make sure that the inside of the cosine function is unitless. So it's not just time that shows up in the parentheses, but some constant, which I have called omega sub s, which is something about the frequency of the motion, but I don't know what exactly it is yet. And then it turns out that x max, the maximum displacement, goes right here. So that is the solution. I talked a little bit about these guys already, but I'll put them up on the screen. So omega sub s is called the angular frequency. It is highly analogous to the angular velocity that we used in circular motion. That's the reason that we have chosen the same letter, the lowercase omega, to represent it. It is related directly to the period, capital T, which is how long it takes for the motion of the block to repeat. So if the block starts way over here and it goes this way and comes back to where it started, that amount of time is the period. Again, analogous to the amount of time it takes to go around a whole circle, and is related to the angular frequency by 2 pi divided by t. We can do a quick spot check to make sure that we indeed have the right solution here. If you plug in this x of t to the differential equation, take a couple of derivatives, you do see that you get this negative sign that pops out. You also, because of the chain rule, get 2 factors of omega sub s. And so when you plug that in down here, we notice that we can leverage this equation to write down what omega is in terms of other quantities that we already know. And it turns out for a mass on a spring that you get that the angular frequency, omega sub s, is equal to the square root of k over m, where again, k is the spring constant and m is the mass of the thing attached to the spring. When you have different things oscillating, you might get different frequencies. We'll see a lot of examples of different things that can be treated as oscillations, and they'll all have slightly different angular frequencies. So you need to know what your system is before you will know what the angular frequency is.